Okay, so now what we're going into, in order to kind of explain everything that we're doing, is we're going to first talk about, hey, contact forces. So yeah, we've talked about contact forces before. Yesterday we talked about, hey, let's draw our force body diagrams or our free body diagrams. I never know which one they want. I hear it both ways, and then it always just gets shortened to FBD. So I don't. It's NBD about the F in the FBD. But so what we want to do really quick is, yes, we have contact forces, but AP wants us to go a little bit deeper, and you're never going to be like having to explain this, but they want you to be able to understand, and kind of this links to your chemistry knowledge, which is cool. But they want you to kind of talk about what causes these contact forces. Like, yes, we have stuff hitting each other. Yes, we have something being like we have a normal force, but why? What's actually causing that? Yes, we can say there's this interaction between these surfaces, but like on a deeper level, like why are they interacting the way that they do? So really our reasoning for this, what's happening, is interatomic forces. So we know from chemistry that everything, all matter, is made up of atoms. And these atoms, so we know from chemistry that all matter is made up of,
Atom.
and these atoms, they have these bonds between them. They have these interatomic forces. So they have these chemical bonds, either weak bonds or strong bonds, depending on the material. But so there's these forces that are happening within those bonds. Those bonds, we can think about them as little tiny forces. And so we call these interatomic forces. So if you're into roots and stem words, inter is between, and then atomic for atoms. And then there's forces that are happening between the atoms themselves. So there's lots of ways we can think about this. Yes, you have all these different models of atoms from chemistry, and you finally land on like the quantum one or Rutherford or whatever. But what we want to think about it as, especially in solids, we want to think of objects being made up of these atoms, and we want to use this ball and spring model. So we want to think about each atom as an actual ball, and then there's this bond between it with a little spring. So you can think about a ball with some springs coming off of it that's attached to another ball. And it would work just like if you had a ball and a spring. If you kind of squished it, it would go together. If you pulled it, it would kind of pull apart, and it would move like a spring would want to do. If you pulled it apart, it would want to be pushed back together. If you pushed it together, it would be want to pull back. Excuse me. So the spring is kind of like the chemical bond, and this idea of having a spring is really important. Everything kind of wants to be in this structure, everything wants to be in its own place. So it's going to do that just like a spring would do. So again, like in this picture down here, we have this hand that's kind of pushing down on it. The actual atoms themselves, just like if you compressed a spring like that, the spring would want to go back to its equilibrium, its natural position, and it would want to push back so it could be back at its normal natural length. So if the hand is pushing down on the surface, the actual surface, those atoms would be pushing back because they want to return to their normal structure, just like a spring and a ball would want to do. So that's how we want to think about all material. So you can think about your hand like this. You can think about surfaces, tables, water bottles, hats, phones, anything. Every object we can think about as being made up of these individual atoms with these springs attached to them. And they are going to compress and stretch just like if you had a bunch of springs in a ball would do. So now when we think about forces, we can really ask ourselves on an atomic level, how would a spring act in this situation? So I kind of just talked about it. But so what the person is doing in this picture, they're compressing the springs. The springs want to be at their equilibrium position. So they would push back on the hand and kind of apply the upwards force on the hand so they could go back to their equilibrium position. And if you pushed on a surface, you know you would feel kind of this push back on you. You would feel an upwards force. And that's exactly what happens and how we can explain it with this model. And now what we're going to do is just really briefly, one, review all the contact forces that we've talked about, and then two, kind of look at it from this new lens, this new ball and spring model lens. So we've talked about tension forces in the past, and we said that a tension force acts when we have a string, a wire, a rope, or really anything that's like a string, a wire, or a rope. So maybe like a cord if you don't have rope at your apartment and you have to use cords and stuff. But so strings, wires, ropes, anything, and they're always going to pull. A string is never going to push on something. That would be very weird if you had a string and you were like, huh, and then it went, ugh. That would be weird. They don't push, they only pull. So strings, wires, ropes, they pull in an object, and the direction of the tension is always in the direction of the string or the rope. So in this picture, I have this string that is going to the right. So the tension force is going to act along that string and to the right. So if we want to use our new kind of ball and spring model, what we can think about, why is it going along the rope? Well, we can look at kind of this microscopic image, go really close and see, oh, what's this string actually made up of? And we say, oh, it's made up of atoms. And we know that these atoms are held in this structure with these bonds, these chemical bonds that are acting like little springs. And if we think about it, when you pull on the very last atom, I didn't draw it, when you pull on that very last one on the rope, it kind of stretches that bond. And then that second atom in line, so this one right here, I'm pointing with my cursor, is like, oh, well, I'm feeling a pull to the right because of this spring, because of that spring. Somebody's pulling on my little spring. So it starts to move to the right. And then it's like, oh, I have a spring on this side. So it starts to stretch that spring. And then that spring starts to stretch the other spring. And then we have this tension force. All of these little objects are going to want to pull in that direction. They're going to pull the object, in this case it was that box, they're going to pull it in that direction. Just like if you had a line of balls and springs. You'd say, oh, I pull on this one, and then we have this according pull throughout the rope. So yes, this is a nice horizontal example, but if we did it at an angle, that would happen. If we did it directly upwards, it would still pull. And we can think about it as this interatomic force, this interatomic exchange. Okay, I covered up the thing that I wanted for normal force. So let me really quickly. Okay, so then we have this contact force. The next one that we're going to look at is normal force. So normal force, as we've talked about in the past, is the force that's exerted by a surface against an object that is pressing against that surface. And the term normal in geometry just means perpendicular. So that's kind of the name of this normal force. So if you see an F and an N, that stands for normal force. A lot of people have this tendency to call it natural force, which is weird, but it's our normal force. And that N is because it's perpendicular. It is perpendicular to a surface. So this normal force is always acting perpendicular to the surface. And if you ever thought, hey, why do normal forces act perpendicular to the surface? I have an answer for you. So we have this box that's sitting on the surface. Here's my box. Here's the surface. They're the same color. We can look at, again, the little microscopic images, the microscopic atoms that are making up the actual surface or the table, whatever we want to think about it as. We can zoom in and say, oh, well, when I put this box on this surface, if I had a bunch of springs that were in this nice like lattice, this ball and springs in this lattice structure, if I put a box on that, it would compress those springs on the top, and those springs would say, oh, dang it, I really wish I was back in my equilibrium position, and they would push upwards to make sure that that happens. They would push upwards, they'd apply this upwards force, because they want to go back to how they are, so they would apply this little upwards push, and that would supply an upwards normal force on our box. So those chemical bonds, the atoms themselves, they don't like being near each other, they like being in that arrangement that they're in, so they're going to push back so they can get back to that arrangement, just like how a spring would want to push back to be in its equilibrium length. So this normal force occurs because you are kind of compressing those springs, and they want to go back to how they usually were. And it happens normally or perpendicularly to a surface. Then the next force that we're going to look at is friction, everybody's least favorite force. So friction, oh, I let this steep for way too long, I left the bag in. That's a darn shame. But so friction is a force that's exerted on an object by the surface, just like the normal force, except for the frictional force is acting always parallel to the surface. So the normal force is perpendicular, the frictional force is parallel to our surface. And it's always going to oppose the direction of motion or the intended direction of motion of an object. So if an object is sliding to the right, the frictional force will be to the left. Or if our object wants to slide to the right, then maybe you're pushing on it, but you don't have enough force to make it move, the frictional force is still going to impose that intended direction of motion. It's going to still act to the left because you want to push it to the right. And with friction, really our main confusion that we had with it, the hardest part, is that there's two types. There's our static friction for when an object isn't moving, and then kinetic friction for when an object is moving. So if we're going to first look at the static friction, This is happening when the object is not moving, and it's going to act opposite. It's going to act to oppose the intended direction of motion. So again, this is a case where object's not moving. So if you want it to move to the left, or if you want it to move to the left, friction is going to act to the right to oppose that. So it can be any value less than or equal to the maximum value of static friction. So this is what really tripped us up. So if you have any object on a surface, so you can take, I don't know, if you put like a pen or a calculator, I'll take this roll of tape and I'll put it down on the surface. There's a little threshold that I have to get to before this thing, that's a terrible example, it's too light. If I have my water bottle, there's this threshold of me pushing until it actually moves. So right now I'm pushing a little bit, pushing more. I eventually reach some stronger force, and then my water bottle actually moved. But up until this point, it was static, it was stationary. It wasn't moving. I don't know if you can see this or not. But so my water bottle, it's not moving. And then eventually I get past that static friction maximum, and then my object will move. So it can be any value that is less than or equal to the maximum value of static friction, and that's why our equation has this inequality. Our frictional force can be anything less than or equal to this coefficient of static friction times our normal force, or our maximum value of static friction. So it's based on the normal force and the static friction coefficient. The coefficient is a constant, and it just tells us about the relative roughness of the surfaces. So how are the surfaces grinding with each other? Are they fitting smoothly, or are they really bumpy? The higher that value, the more rough our surface is. And so then if our force, or if our object isn't moving, the static friction force is just equal to the net opposite force that's opposing that frictional force. Excuse me. So that's worded a little bit weirdly, but if again I have my water bottle, and I'm saying, okay, here's my water bottle. Let's say I'm pushing with 1 Newton. The frictional force is also 1 Newton. It's opposing my 1 Newton push, because right now my net force is 0. If I push with 2, now it has a frictional force of 2. And then if I push 3, the frictional force is pushing back with 3, because there's no net force acting on that object. So that's our static friction. And then kinetic is for when an object is actually moving. It's going to act to oppose the direction of motion, and it is a singular value that does not depend on how fast the object is moving. So kinetic friction is just going to be one value. It's not a range, it's not an inequality, it is just one singular value. And that value is always equal to just our coefficient of kinetic friction times the normal force. So with this, when we're dealing with kinetic, our equation is a little bit weird, but it's not this inequality part, it's just the equal part. And the coefficient, again, is constant, and it's based on the material of the surfaces. So once we overcome this realm of static friction, if we kind of have this image here, once we push harder, so on our x-axis we have applied force, and then we have the frictional force. If we push harder than our maximum, then we overcome this threshold, and then we're allowed to move, and then we have this one singular value of kinetic friction. So hopefully that's kind of ringing some bells. And then if we want to look at this on one of those atomic levels, I kind of did a bad job drawing it, but so I didn't draw this box. But so this box and the surface, they have this bumpiness to it. Everything's not completely smooth. Everything has some sort of weirdness and imperfections at its surface. If we get on a microscopic level, even if it feels smooth, there's still atoms that are kind of bumping up. So we have this bumpiness, this rigidness, and that's not just nothing, there's atoms in there. So if we have these little atoms that are up here causing these bumps, I didn't draw the bumps for the box, but it would also have these atoms. I just didn't draw them. So we have this surface, it's got these little bumpiness, these little atoms that are protruding to cause the rigidness of the surface. And then we have the surface of the box. If we were going to move this box, this top thing, to the right, it would cause our atoms to compress to the right as well. So we kind of squish them like that, and they would push back because they don't want to be pushed like that. So it's causing this force that's opposing the direction of motion. So it wants to push them to the right. These start to compress to the right. These springs will compress, and they say, hey, I don't like being compressed. I want to be back to how I was. And they're going to kind of stretch or push so that they can go back to being that normal equilibrium length, have that normal length between them. And then if you push down harder, if you increase that normal force, then you're engaging more of these to push horizontally. So I don't know if that makes sense, but if you took the surface and you push it harder, you'd be engaging not just like this top layer of atoms, you'd be getting down here to get a lot of these bottom layers, and you'd have more pushes to the left. So you'd have more of these atomic forces acting horizontally parallel to the surface. And then the final one, we have the spring force. So it acts in a way such that the spring will return to its natural position. This is kind of like we were just talking about with everything else. So if you compress the spring, it will push so that it will be uncompressed. If you stretch the spring, it will pull so that it can be unstretched. The equation for spring force is just going to be the spring constant K and the amount that you stretch it. And I'm not going to draw this on the microscopic scale just because it would look like a spring, just like we drew. But our equation for this is our spring force equals our coefficient, our spring constant, times x. And just a little diagram for that. So here's our equilibrium length. If we pull it away from the equilibrium length, the force will say, hey, no, I want to be back to this dotted line. I want to be back to where I was. If I compress it, the force will say, nope, I want to go to the right. I want to be back to this dotted line to be back to where I was. So that's our contact forces. I'm going to stop this video here, and then I'll see you in the next one.